Imagine the clock strikes midnight on Black Friday, your traffic surges 100x. Suddenly, your high-performance database cluster, which worked perfectly during staging, hits a brick wall. P99 latency spikes from 10 ms to 5 seconds. You scale CPU and RAM, but nothing helps. Why? Because you have hit the invisible wall of storage engine internals. In many cases, this is caused by hidden write amplification, where the database is doing 50 times more internal I/O than the actual data you are sending. Without knowing whether your engine uses a B-tree or an LSM-tree, you are essentially flying a plane with a broken altimeter. Most developers treat the DB as a black box that magically persists data, but when the scale hits a certain threshold, the internal mechanics, the compaction cycles, the page splits, and the wall bottlenecks become the only things that matter. By the end of this lecture, you will possess the X-ray vision required to see through these abstractions. In modern software engineering, we are taught to value abstraction. We use ORMs, cloud-managed databases, and simplified APIs. However, as Joel Spolsky famously stated, all non-trivial abstractions, to some degree, are leaky. When you execute a simple update command, it isn't just a row change, it's a complex dance of MVCC versioning, transaction log flushing, and buffer pool management. Relying solely on the black box approach leads to catastrophic architectural failures because you cannot optimize what you do not understand. A true expert knows that every design choice is a trade-off. Choosing PostgreSQL over MySQL or DynamoDB over MongoDB should not be based on popularity, but on an intimate understanding of their internal engines. The difference between a standard developer and a top-tier architect is the ability to diagnose an abstraction leak during a crisis. This knowledge is precisely what distinguishes those who merely use technology from those who build and lead world-class systems. But is it even possible to master these complex subsystems in one go? Let's break down the roadmap. To master database internals, we must focus on the 4 pillars that govern every modern data system. First, storage engines, the fundamental structures like B-trees used in PostgreSQL and InnoDB versus LSM-trees used in RocksDB or Cassandra. Second, concurrency control, specifically MVCC, which allows reads and writes to happen simultaneously without locking. Third, distributed transactions, how we maintain aside properties when data is spread across multiple nodes using protocols like two-phase commit. And finally, consensus, the Raft and Paxos algorithms that ensure all nodes agree on the state of the world even during network partitions. These are not just academic concepts. They are the heart of the professional engineer exam for information management and the core of high-level system design interviews. Each pillar represents a critical decision point in your architecture. If you miscalculate one, the entire system can become inconsistent or unavailable. Do you think these pillars act independently? In reality, they are deeply intertwined, and a change in one often necessitates a trade-off in another. By the end of this course, you will transform from a database user into a database architect. You will be able to analyze workload patterns and decide precisely which storage engine suits your write-heavy or read-heavy requirements. You will understand how to tune MVCC isolation levels to balance performance and data integrity. Furthermore, you will gain the skills to design distributed systems that remain resilient under the CAP theorem's constraints. For those preparing for professional certifications or senior-level interviews, this lecture provides the structured logic needed to answer complex why questions, not just how questions. We will move beyond the surface-level syntax and dive deep into the binary level where data meets the disk. We are building a skill map that will serve you for the next decade of your career, regardless of which specific database product becomes the next trend. But to truly understand these pillars, we must start at the very beginning, the fundamental battle over how data is physically arranged on the disk. In the next chapter, we dive into the storage engine wars where B-trees and LSM-trees fight for supremacy. In the world of relational databases like PostgreSQL and MySQL, the B+tree reigns supreme as the gold standard for indexing. Its primary strength lies in its page-based structure, where data is organized into fixed-size blocks, typically 8 KB or 16 KB. When a new record is inserted, the engine traverses the tree to find the correct leaf node. If that page is full, a page split occurs, rebalancing the tree to maintain its sorted order. This in-place update model is what makes B-trees exceptionally fast for point lookups and range scans, as the physical proximity of data on disk often matches its logical order. However, this architectural choice creates a rigid structure that requires constant maintenance to keep the tree balanced and the pages optimized for read performance. But what happens when we start modifying data that is scattered across different physical locations on the disk? The efficiency starts to crumble under a specific type of pressure. The biggest Achilles heel of the B-tree is its reliance on random I/O. Because the engine performs in-place updates, it must jump to different physical disk addresses to modify specific pages. In high concurrency OLTP environments with heavy write workloads, this results in massive disk head movement or SSD controller overhead, leading to significant latency spikes. Furthermore, as records are deleted and updated, fragmentation or page bloating occurs. You might have a 16 KB page that only contains 4 KB of actual data, yet the database must still read the full 16 KB into memory. This inefficiency is the silent killer of performance in aging databases. While B-trees are perfect for reading, they struggle when the write-to-read ratio shifts towards heavy ingestion. To prevent data loss during these complex disk operations, we rely on a critical safety mechanism, but even that comes with a performance tax. Because writing a full data page to disk is an expensive and risky operation, modern B-tree engines use write-ahead logging or WAL. Before any change is made to the actual data file, a small sequential log entry is appended to the WAL file. This ensures durability. If the system crashes, the engine can replay the WAL to recover the state of the data pages. This process, combined with checkpointing where dirty pages in memory are periodically flushed to disk, allows the B-tree to offer ASI compliance. However, even with WAL, the core problem remains. Eventually, the engine must perform those random writes to the main data files. As data volumes exploded in the era of big data, the industry needed a way to turn those expensive random writes into cheap sequential writes. This leads us to a radical architectural shift that powers the world's most scalable write-heavy databases. Log-structured merge trees, or LSM trees, take the opposite approach of B-trees. Instead of trying to update data in place, they treat all writes as sequential appends. When data comes in, it is first written to an in-memory buffer called a memtable, which is typically an ordered structure like a skip list. Once the memtable reaches a certain size, it is frozen and flushed to disk as an S table, sorted string table. These S tables are immutable. They're never modified. This means the disk only ever performs high-speed sequential writes, which is the fastest possible way to interact with any storage medium. This architecture, popularized by Google's Bigtable and used in RocksDB and Cassandra, eliminates the random write bottleneck entirely. But if we never update anything and only keep adding new files, how do we actually find a specific record without searching through hundreds of files on disk? Since LSM trees store data across multiple immutable S tables, a single read might theoretically require checking every single file. This is known as the read penalty. To solve this, LSM engines use two ingenious techniques: compaction and Bloom filters. Compaction is a background process that merges multiple SS tables, discarding old versions of records and tombstones, markers for deleted data, to reclaim space. To speed up point lookups, a Bloom filter, a space-efficient probabilistic data structure, is kept in memory. Before checking the disk, the engine asks the Bloom filter, does this key exist in this S table? If it says no, the engine skips the file entirely. This prevents unnecessary disk I/O with nearly 100% accuracy for negative hits. However, the background compaction process itself isn't free. It consumes CPU and I/O cycles, leading to a phenomenon that every system architect must understand. While LSM trees excel at write throughput, they suffer from write amplification. This means that a single piece of data might be written to disk multiple times as it moves through different levels during compaction. Engineers must choose between two main strategies: leveled compaction and tiered compaction. Leveled compaction, used in RocksDB, minimizes read amplification by keeping each level sorted and non-overlapping, but increases the number of times data is rewritten. Tiered compaction, common in Cassandra, is much friendlier to write-heavy workloads, but makes reads more expensive as it allows overlapping SS tables. Choosing the wrong strategy can lead to I/O starvation, where the system spends all its resources just moving old data around instead of processing new requests. There's no free lunch in storage design. It's always a trade-off between read speed, write speed, and space efficiency. To conclude our deep dive, let's look at the definitive decision matrix. B-trees are your best bet for general-purpose OLTP workloads where read performance is critical and data fits neatly into relational structures. They provide predictable read latency and efficient range queries. On the other hand, LSM trees are the powerhouse for high-velocity data ingestion, such as logging time series data or massive-scale NoSQL environments. If your workload is 90% to writes, B-tree's random I/O will eventually choke your hardware, while LSM tree will hum along by utilizing sequential I/O. However, you must be prepared to manage the operational complexity of LSM compaction. Understanding these internals is what separates a senior architect from a junior developer, knowing that the best engine depends entirely on the shape of your data and the behavior of your users. But what happens when we need to combine these storage models with real-world business requirements? We've deconstructed the engines, but the engine is only half the story. In practice, choosing between MySQL's InnoDB, B-Tree, and a solution like MyRock's or ScyllaDB LSM-Tree can make or break your infrastructure's scalability. Remember, B-trees favor the reader, while LSM trees favor the writer. As you move forward in your career as a DBA or architect, always ask, what is the I/O pattern of this application? Don't just follow the hype of NoSQL or the tradition of SQL. Look at the disk access patterns. We have mastered how data is physically stored and retrieved, but there's a ghost haunting these engines: the problem of consistency. Even if the storage is fast, how do we handle multiple users trying to edit the same record at the same time? That is the nightmare of concurrency control, and in the next chapter, we will confront the ghost of MVCC to see how databases manage multi-user access without locking up entirely. In the early days of database design, we relied heavily on pessimistic locking, specifically two-phase locking or 2PL. While mathematically sound for consistency, 2PL is a scalability nightmare in modern multi-core environments. When a transaction holds an exclusive lock for an update, all other readers and writers are blocked, leading to massive lock contention and the dreaded convoy effect. In high-traffic systems like global e-commerce platforms, these wait states translate directly into latency spikes and underutilized CPU resources. We need a way to let readers proceed without being held hostage by long-running writers. This fundamental limitation of the locking model is what forced the industry to move toward a more optimistic, version-based approach. But how do we maintain consistency without global locks? The answer lies in how we manage multiple versions of the same data simultaneously. If we can't lock the data, we must create a temporal copy of it, but this choice introduces a whole new set of architectural challenges that we will explore right now. Multi-version concurrency control, or MVCC, is the ghost in the machine. Instead of overwriting a row in place, the engine creates a new version of that row. When a transaction starts, it is assigned a unique snapshot or transaction ID. Every record in the database then carries metadata like xmin, xmax in PostgreSQL to define its visibility. When a reader queries a table, it doesn't see the latest physical data. It sees the version that was valid at the moment its snapshot was created. This ensures that readers never block writers, which is the golden rule of modern database performance. Whether it's MySQL's in a DB using rollback segments or PostgreSQL using dead tuples in the main heap, the core principle is the same: time traveling through data versions. But maintaining these ghost versions isn't free, and the way different engines track these versions determines their performance profile under heavy write load. Does this mean we have solved all concurrency problems? Not quite, because the next logical question is how we define exactly which ghost a specific transaction is allowed to see. How does MVCC map to the ANSI SQL standard isolation levels? This is a critical area for both system design and technical exams. In read-committed mode, a new snapshot is taken at the start of each individual query. In repeatable read, the snapshot is taken only once at the start of the transaction. Interestingly, while the SQL standard suggests that repeatable read may allow phantom reads, most MVCC implementations like PostgreSQL and MySQL's InnoDB effectively eliminate phantoms even at the repeatable read level using snapshot isolation or gap locking. However, this level of consistency comes with a trade-off called write skew. This occurs when two transactions read the same data, modify different records based on that data, and commit violating a logic constraint that neither could see. Understanding these nuances is what separates a senior architect from a junior developer. We've seen how MVCC grants us immortality of data versions, but every ghost must eventually be laid to rest. What happens when these old versions start piling up and choking your storage? That is where the hidden operational cost of MVCC reveals itself. MVCC creates dead tuples old versions of data that are no longer visible to any active transaction. The way these are cleaned up defines the fundamental operational difference between PostgreSQL and MySQL. PostgreSQL uses a copy-on-write approach in the main heap, meaning old versions stay in the data pages until a process called vacuum removes them. If vacuum can't keep up, your table files grow massively, a phenomenon known as table bloat. In contrast, MySQL's InnoDB uses an undo log or rollback segment. It keeps only the latest version in the main page and moves the old versions to a separate undo space. While MySQL avoids some heap bloat issues, it places a heavy burden on the purge thread and undo logs during massive updates. Both engines face the same ultimate reality: you cannot keep versions forever. If a single long-running transaction stays open, it prevents the engine from cleaning up any versions created after it started. This is the SHAP1 cause of performance degradation in production databases. But what if the cleanup doesn't just slow down your DB, but threatens to stop it entirely? Every DBA's nightmare is transaction ID, TXID wraparound. In systems like PostgreSQL, the TXID is a 32-bit unsigned integer, meaning it caps at about 4 billion. Because MVCC uses these IDs to determine visibility, if the counter wraps back to 0, transaction from the past might suddenly appear to be in the future, making all your data effectively invisible. To prevent this catastrophe, the database must periodically freeze old rows, marking them as permanent so they no longer rely on specific TXIDs. This freeze vacuum is an intensive I/O operation. If your database reaches the auto-vacuum freeze max age without completing this process, the engine will enter a read-only safety mode or shut down entirely to prevent data corruption. This is a critical failure state that has taken down many major tech companies. Monitoring your oldest transaction age isn't just a best practice, it's a survival requirement. Now, even if you manage your TXIDs perfectly, there is another subtle killer: the impact of MVCC on your indexes, which can lead to a 10x performance hit if not optimized. In a standard MVCC update, when a row is updated, every index pointing to that row must also be updated to point to the new physical location. This causes massive index bloat and write amplification. To combat this, PostgreSQL introduced heap-only tuple or HATE updates. If an update doesn't change any index columns and there is enough space on the same data page, the engine creates a chain. The index continues to point to the old version, the root, which then points internally to the new version on the same page. This bypasses the need for index entry modifications and significantly reduces the overhead of frequent updates. However, for ATIA to work, you must have enough fill factor empty space left on each page. Without proper tuning of the fill factor, your highly indexed tables will suffer from performance degradation as the database struggles to maintain version chains across different physical pages. This brings us to the ultimate realization. MVCC is a game of balancing storage space against transactional throughput. How do we summarize these complex trade-offs into a coherent architectural strategy? Let's wrap up this chapter and find out. We have unmasked the ghost of MVCC. We've seen how it liberates us from the shackles of pessimistic locking, allowing modern databases to scale to thousands of concurrent users. But we've also learned that this freedom comes at the price of storage management. From the visibility rules of XMAX to the operational risks of TXED wraparound and the performance tuning of ATI updates, mastering MVCC is about managing the hidden depth of data versioning. As an architect, your job is to balance the trade-offs, choose your isolation levels wisely, monitor your vacuum health, and tune your storage parameters to prevent bloat. But what happens when your data outgrows a single machine? Can these versioning principles survive across a distributed cluster where time itself is unreliable? In the next chapter, we dive into the complex world of distributed transactions, where the challenges of MVCC meet the chaos of network partitions and consensus algorithms. Get ready for scaling out distributed transactions. In a monolithic database, atomicity is guaranteed by a local write-ahead log, but when data is partitioned across multiple nodes, ensuring an all-or-nothing outcome becomes a massive challenge. This is where the two-phase commit, or 2PC, protocol enters. In the prepare phase, a coordinator asks all participants if they can commit. Only if every single node responds with a yes does the coordinator move to the commit phase. This is the foundation of the XA standard used in MySQL and PostgreSQL. However, the performance cost is high because every participant must hold on to row locks until the final decision is reached. Even a single slow node can bottleneck the entire cluster's throughput. While it guarantees strict consistency, it is the enemy of low latency scaling. But what happens if the coordinator vanishes midstream? The system enters a dangerous state of uncertainty. The fatal flaw of 2PC is its blocking nature. If a participant crashes after voting yes, but before receiving the final decision, it remains in an in-doubt state, holding locks indefinitely. More critically, if the coordinator fails, the entire transaction is orphaned. This is a classic single point of failure. In high concurrency environments, these synchronous locks lead to lock contagion, where a single stalled transaction cascades into a full system halt. Experienced architects often avoid 2PC for high-volume public-facing APIs due to this availability risk. This trade-off between consistency and availability is a core theme in the CAP theorem. If absolute consistency is too expensive, we need a way to trade it for availability. Enter the world of microservices. To solve the availability problem in distributed systems, we often turn to the Saga pattern. Unlike distributed ACAD transactions that hold locks across nodes, Sagas treat a business process as a sequence of local transactions. Each step updates its own database and triggers the next step via an event or message. If a step fails, the Saga executes compensating transactions to undo the previous steps, like a refund following a failed shipping request. This follows the eventual consistency model. Sagas excel in microservices because they don't require long-lived locks, thus maximizing throughput. However, they lack isolation, meaning dirty reads are possible across different steps of the Saga. Sagas handle long-running flows, but for high-precision financial logic, there's another pattern you must know. The try, confirm, cancel, or TCC pattern provides a middle ground for distributed consistency at the application level. In the try phase, we don't just lock rows, we reserve resources, such as deducting from available balance and adding to reserved balance in the application logic. The confirm phase then finalizes the reservation, while the cancel phase releases it. This is highly effective because it moves the locking logic from the database engine to the business domain, avoiding low-level deadlocks. TCC is common in complex payment gateways and booking systems where you cannot afford to block a database for seconds. While powerful, it requires double the coding effort to implement every operations inverse. All these patterns require complex application logic. Wouldn't it be better if the database itself handled consensus automatically? Modern distributed databases like CockroachDB and TDB have moved away from manual 2PC coordination towards consensus algorithms like Raft. Raft simplifies the complex Paxos algorithm by focusing on a strong leader. The leader is responsible for receiving client writes and replicating them as log entries to followers. A write is only considered successful once it has been appended to the logs of a majority of nodes. This log replication ensures that even if some nodes fail, the state of the database remains consistent across the cluster. Raft's genius lies in its clear term-based leader election, which prevents the split-brain scenario where two nodes think they are the boss. Reliability depends on more than just a leader. It depends on the power of the majority. The principle of quorum is the bedrock of distributed resilience. In a 5-node cluster, a quorum is 3. This means the system can tolerate the failure of 2 nodes without losing data or availability. Quorum ensures partition tolerance if a network split occurs. Only the partition containing the majority of nodes can continue to process writes, while the minority partition becomes read-only or halts. This prevents conflicting data from being written to both sides. Unlike 2PC, which requires 100% availability for a commit, Raft-based systems only require a simple majority. This architectural shift significantly improves the reliability of cloud-native databases. This theory isn't just for white papers, it's the backbone of the most resilient databases in production today. How do modern new SQL engines like CockroachD or TDB apply this at scale? They use a multi-raft architecture. Instead of one giant raft group for the whole database, they divide data into small ranges or regions, typically 64 MB to 120 MB. Each range has its own raft group with its own leader and followers distributed across different racks or even geographical regions. When you write a record, only the raft group responsible for that specific range is involved. This allows the database to scale horizontally to hundreds of nodes and petabytes of data while maintaining ASA properties without the global performance penalty of 2PC. By combining consensus and sharding, we reach the holy grail of distributed systems, linearizability. To wrap up this deep dive, we must understand the gold standard of consistency, linearizability. It ensures that once a write is acknowledged, any subsequent read will return that value or a later one, regardless of which node you query. Achieving this in a distributed world requires perfectly synchronized clocks or logical timestamps. We've compared the legacy 2PC, the flexible Saga TCC patterns, and the modern Raft-based NewSQL approach. Choosing the right one depends on your consistency vs. latency budget. Scaling the transaction is one thing, but how do we apply this in a high-traffic production environment? In the next chapter, we look at real-world architecture adoption and how to choose the right engine for your specific workload. In traditional RDBMS environments, scaling out was often hampered by the tight coupling of compute and storage. This architecture forced us to replicate the entire data volume to every read replica, causing massive I/O overhead and replication lag. Amazon Aurora fundamentally changed this paradigm by introducing the log as the database philosophy. By offloading the logging and storage layers to a multi-tenant, scale-out fleet, Aurora eliminates the need for traditional buffer pool flushing and heavy redo log application on the compute nodes. In this model, only the redo log records are sent across the network, significantly reducing traffic and enabling sub-minute failover and rapid scaling. This shift from server-bound storage to cloud-native, distributed storage is the cornerstone of modern high-availability design. Experienced architects must understand that this isn't just a marketing gimmick. It's a structural solution to the right amplification and consistency bottlenecks we discussed in earlier chapters regarding MVCC and B-Tree locking. But as we move toward these massive cloud-native clusters, how do we handle the shift from pure transactions to real-time insights without killing our performance? Let's look at how modern engines bridge this gap. For years, we were forced to choose between OLTP for transactions and OLAP for analysis, often relying on slow ETL processes to sync the two. Hybrid Transactional Analytical Processing, or HTAP, breaks this silo. Consider the TDB architecture with TFlash. It utilizes Raft-based replication to maintain both a row-based engine for point lookups and a columnar-based engine for analytical scans simultaneously. When a query comes in, the cost-based optimizer determines whether to hit the B-Tree-like row store or the LSM-Tree-inspired columnar store. This ensures that heavy analytical queries don't consume the resources needed for your mission-critical transactions. From an information management engineer's perspective, this solves the data freshness problem, allowing businesses to run real-time fraud detection or inventory analysis on live production data. This integration is no longer a luxury. It is becoming a standard requirement for data-intensive applications. But wait, does this mean we should use HTAP for everything? The answer lies in the trade-offs we choose to accept. I will show you exactly how to evaluate these trade-offs in the professional decision matrix next. Selecting a database isn't about finding the best one, it's about finding the right one for your specific workload characteristics. In professional system design, we use a structured 10-point checklist to evaluate the internal engine's suitability. We look at the read-write ratio. If it's write-heavy, we lean toward LSM trees. If it's read-heavy, B trees remain king. We evaluate the consistency requirements. Do you need strict serializability, or is eventual consistency acceptable for your scale? We also consider the operational surface area. How much manual tuning does the vacuuming or compaction process require? For technical exam candidates, this framework is the golden key to answering architectural design questions. You must be able to justify why you chose a distributed KV store over a traditional relational model based on throughput, latency SLAs, and data growth projections. Many developers fail here because they follow trends rather than metrics. Now, while technical purity is important, we must eventually face the reality of the business world, the return on investment. If perfect technical solution costs 10 times the budget, is it still the right solution? Let's wrap up with the strategic view on cost versus performance. The ultimate goal of a database architect is to balance technical excellence with business reality. We've explored B-trees, LSM trees, MVCC, and distributed consensus. These are the tools in your belt. However, the best architecture is the one that meets the SLA at the lowest total cost of ownership, TCO. In the field, I often see teams over-engineering with complex distributed databases when a well-tuned PostgreSQL instance on a larger instance would have sufficed for years. Remember, every layer of distribution adds a complexity tax in terms of monitoring, debugging, and maintenance. As we conclude this chapter, reflect on the core themes. Understand the internals so you can predict where they will break. Don't treat the database as a black box. By knowing how the pages are structured and how the locks are held, you move from being a user to being a master of the system. we have covered the how and why of modern database engines. In our final chapter, we will synthesize everything we've learned into a clear roadmap for your career. We are going to look at the architect's path, how to stay relevant in an era where AI and automation are beginning to manage the very engines we just deconstructed. As we wrap up our journey through database internals, it is crucial to map these complex concepts to the high-level framework of professional architectural design and technical certification. In the field, you shouldn't just ask which database should I use, but rather which internal mechanism solves my specific performance bottleneck. For instance, when designing for high write throughput in a logging system, your mind should jump to LSM trees and write-ahead logging. When consistency is the priority in a global distributed environment, the choice between 2PC and Paxos becomes your core blueprint. This table summarizes the key pillars we have covered: storage structures, concurrency control, and distributed consensus. Mastering these keywords allows you to communicate with senior engineers and stakeholders using a shared, precise technical language that distinguishes a true expert from a casual user. Understanding the way behind these structures is what truly prepares you for high-level system design and professional certification exams alike. But how do we transform this raw knowledge into a philosophy that guides your entire career? The path of a database architect is not about memorizing commands, but about understanding the trade-offs of the engine's heartbeat. We have opened the black box of B-trees, dissected the layers of MVCC, and navigated the complexities of distributed transactions together. In the industry, many developers remain users of tools, but the real seniors are masters of internals who can predict how a system will behave under extreme load. Remember, there is no silver bullet in database design, only the right tool for the right context, chosen through deep technical insight. Continue to read academic white papers, dive into the open source code of major engines like PostgreSQL or MySQL, and never stop questioning why a system was designed a certain way. Your ability to see through the abstraction layers is what will define your value in the era of massive data and complex cloud architectures. This concludes our deep dive into the secrets of database engines. The next step is yours to take in the real world of production systems. Go forth and design with precision.